So those are our two goals for pre-calculus. You want to be able to solve everything, and we want to be able to graph everything. When you put it in those terms, that's pretty simple, right? Everything that we're going to do for the entire semester is going to be focused on one of those two things: solving everything and graphing everything, all with an eye towards what is that going to help us in calculus, or how is that going to help us in calculus. And you're not going to get that answer yet, but you know we're working towards it, and we're taking care of all the baseline stuff that you're going to need, so that when you do take that calculus class, it all makes sense, and you can do everything that you need to do to answer the question, to solve the problems that are posed in that course. Okay, so we're just kind of building up to that culminating course in calculus. But this lesson is really focused on being able to graph everything. And if you remember, I told you in aptitude trig, you graphed a lot of these functions, but you did it in isolation. You graphed quadratics when you did that unit. Then a few weeks later, you graphed square roots when you did that unit. Then a few weeks later, you graphed logarithmic functions when you did that unit. But you didn't see any similarities or any connections from one graph to another. You just viewed all of them as just separate and distinct graphs. But in reality, these transformation rules that we learned yesterday apply to all functions. Okay, all of our algebraic functions, all of our trigonometric functions, logarithmic functions, exponential functions, any kind of function that we can come up with, these rules for transformations apply to all of them. So it makes more sense to me that in pre-cal, now that we have a little bit of a background knowledge, that we apply all of these transformation rules at the same time. And that's what we're doing, is we're going to see how can I graph any kind of algebraic function, and we're going to today focus on our algebraic functions, using these transformation rules that we learned yesterday. Okay, so, you know, the algebraic rules that we've discussed are our absolute value function, our quadratic and cubic function, our square root and cubic root functions. And then, of course, we have the greatest integer function and the rational or reciprocal functions. There is one more algebraic function, that's the semicircle. But we're going to kind of hold off and deal with that next week. So we can kind of, because we're going to treat it a little bit differently, although the rules will still apply to it. All of these are our algebraic functions. And there's really not any other algebraic function that you can think of that would not fall under one of these umbrellas. Okay? All of these functions here are put together by addition, subtraction, and multiplication, division, and exponents, and radicals, and absolute values. That's all algebra. And so no matter what combination we try and use, it's going to fall under one of these umbrellas of these parent functions. And so what we're going to do is we graph these functions using our parent function. We're going to start by identifying the parent function. Now, on the homework last night, I gave you that function to start with. You didn't have to do any thinking. You didn't have to do any considering. You didn't have to think about what points might be on a particular function. All that was given to you. I said, here's the graph that I'm going to call f of x, and it has points on it that you could identify by just looking at the x and y coordinates. But today, I'm just going to give you the equation. I'm not going to get you started with the graph. I'm just going to give you the equation. And what you're going to have to do is, based on the equation, you're going to have to decide what's the parent function, and then what are some points that are on that parent function. Okay? Somebody asked, earlier in the week, do I have to memorize that entire flip book? Well, yes and no. I mean, do you need to memorize it word for word exactly? I hope not, because I hope that if you have enough of an understanding of what the graph looks like and what some points are that are on that graph, then you can tell me about the domain and the range and the asymptotes and the symmetry and one-to-one and in behavior and all that kind of stuff. Okay? But yeah, you do need to know that when you look at a square root function, you need to know what its graph looks like. What is its general shape? You need to know what are some points that are on that graph. I would hope that when you think about the square root function, you immediately think 0, 0, 4, 2, 9, 3, and 1, 1. Okay? Those are all points that are on that graph. When you see the cubic function, I hope that you immediately think -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. Because if you know those points, then we can take these transformation rules where we reflect, or where we shift, or where we stretch or shrink a graph. We can apply those transformation rules to those points on that parent function, and then we've gotten our new graph. Okay? And so that's what we're going to practice with today. think I've broken this up by, several examples of each type. And we're not going to do every single example. We'll do one or two from each set. And then, I'll give you some that just kind of have them all mixed together. This first set are just linear and absolute value functions. I'm not going to insult your intelligence by making you graph a linear function. It's just a line. If you can't do that by now, then you're probably in the wrong class. You probably meant to go to Algebra 1. But we know how to graph lines, so we're good. The next few are absolute value functions. Let's just pick one. Let's do number 3. We have negative 3y minus 2 equals 6 times the absolute value of x minus 5 minus 9. What's the first thing that we're going to have to do? You're going to get y by itself, right? And we can't graph this. You couldn't put it on your calculator unless you got y by itself. So if the function's given without having y by itself, we got to start there. So we'll add the 2 over. How would y'all feel about making this like negative 8? Let me do that. Feel a little bit better about that. Right? So when I add the 2 over, that adds to this negative 8, which makes it negative 6. And then what do we have to do? Yeah, divide by the negative 3. So as we do that, we'll have negative 3y equals 6 times the absolute value of x minus 5 minus 6. Remember, we made that an 8. We added 2 over. And then when I divide by negative 3, I'm going to divide this coefficient by negative 3. I'm going to divide this negative 6 by negative 3. Okay? So I've got to divide, everything on both sides of that minus sign by negative 3. But if I just divide this coefficient by negative 3, that takes care of it. So I have y equals negative 2 times the absolute value of x minus 5 plus 2. All right, what all are we going to do to the parent function based on that equation? All right, 5 to the right, that's going to be the first thing that we do. What now? All right, reflect it over the x-axis and multiply the y's by 2, or just multiply the y's by negative 2, and that'll take care of both of those at the same time. And then what? 2 up. Those are our rules, and that's the order in which we're going to get it. Okay. Now, again, last night on the homework, I gave you the graph, so you easily identify the points. I'm not giving you the graph this time. I'm giving you the function. And so what's our parent function? Absolute value. What we know immediately is that for the absolute value function, it includes the points negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. So there's other points, but those 5 would be enough to graph the absolute value function. And all I have to do now is apply these rules to these points. So negative 2, 2. I'm going to take that point and I'm going to move it 5 units to the right. Then I'm going to take the y coordinate, which is currently 2, and multiply it by negative 2, which would give me negative 4. And then I'm going to shift it up 2 units. And so now there is where that point is located, which would be a 3, negative 2. So I've taken that first point and I've shifted it. Next point is negative 1, 1. Is right here. Same thing. 5 units to the right. Take the y coordinate, multiply it by negative 2. Then shift 2 units up. Zero, 0. 5 units to the right. Multiply the y coordinate by negative 2. Still 0. Move it up 2. part, here's what this graph looks like. Remember, the absolute value function has symmetry, so if this is our vertex, which was the 0, 0 point that we transformed, then there's symmetry on either side of that, which can make it a little bit easier to graph. So there would be that absolute value function. What's its domain? Yeah, negative infinity to positive infinity. What's its range? Negative infinity to 2, or all the y's such that y is less than or equal to 2. It does have symmetry, just not to either the x-axis or the y-axis anymore. It has symmetry to the line x equals 5, but it's not going to be even or odd anymore because it has to be specifically symmetric to an axis for it to be either even or odd. It's not one-to-one. We can talk about its end behavior, and that as x approaches negative infinity and positive infinity, both y's are approaching negative infinity. Does it have an absolute maximum or an absolute minimum? It has an absolute maximum of 2 when x is 5. And we know it's a maximum because the function changes from increasing to decreasing at that point. So it demonstrates a lot of the same characteristics as the parent function. It's just been moved a little bit. Okay, let's move on to the next set. These are our quadratic and cubic functions. So let's try number 3. It does look like we're going to have to get y by itself. So what am I going to have to do to get y by itself? Right, so I'll divide negative 6 by 2, which will take care of all of this. And then I'm going to divide 5 by 2. So I'm going to have y equals negative 3 times x minus 4 squared minus 5 halves. So tell me everything that we're doing to this parent function. 4 to the right. By y by negative 3. And then moving 5 halves down. That's 2.5, right? What's our parent function? Yeah, y equals x squared. And hopefully we know some points on that. We use these same points that we've been using. What's the y coordinate at negative 2? 4, same thing, it's positive 2. And then at negative 1 would be 1, and 0, 0. So those are the points that we're going to use, and we're going to apply these transformations to these points. So start with negative 2, positive 4. Move it 4 to the right. Take a y coordinate, which is currently 4, multiply it by negative 3. That'll put it down here at negative 12. And then move it down 2.5 more. So what would that be, like at negative 14.5? All right, negative 1, 1. Four to the right. Multiply the y coordinate by negative 3. Well, it's currently 1, so that would put me at negative 3. And then move it 2.5 units down. So there's 1, there's 2, there's a half. Next point is 0, 0. And remember, if it helps, that's the vertex of the parent function. And remember, the graph is symmetric about that vertex for a quadratic function. So once I find this point's placement, I should be able to do some symmetry. So I'm going to move 4 units to the right. Multiply the y coordinate by negative 3. That's going to leave it at 0. And then move it down 1, 2.5. This point is its reflective point, and same thing here. And then we just draw in our parabola. little hang up about that vertex for a parabola, that it's got to be rounded. So don't make it look like an absolute value. Everybody okay? All right, you try 4 and 5. And remember, provided that you solve for y correctly, you shouldn't get this wrong because you have a calculator, right? So graph it by hand, and then go to your calculator and make sure that the graph from your calculator matches what you found when you graphed it by hand. All right, so I went ahead and solved them for y for you. These do have a vertical shift that both are going to be a little bit ugly, but at least that's the last thing that you're going to do on the graph. Everything else sticks with integers primarily. But at number 4, I solved for y, so I subtracted that 2 over from the 3, and then I divided by -4. So the 2 in front of parentheses divided by -4 gave me -1/2, and then the 1 that was left over gave me the -1/4 at the end. It's a quadratic function, so we know that those are the points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4 that we're going to use. And then as we transform this, what we're going to do first is we're going to shift 1 unit to the right. Then we're going to multiply all the y coordinates by -1/2. And then we're going to move down 1/4 of a unit. Okay? And you know, as I said, use your calculator to make sure you got that right. So after you graphed it by hand, then you'll go to your calculator and put that y equals in and make sure that the graphs match. If they don't, then look, you know, at the individual points to see if maybe you accidentally just messed up one point and that threw your graph off. Okay. On number 5, I solved for y by dividing by 3. But notice this is a cubic function, so you really got to pay attention to the function because that slight difference in the exponent means it's a completely different function. And now we're using the points -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. And we're going to take each of those points and move it 4 units to the left. We're going to multiply the y coordinates by -1, which is going to reflect it over the x-axis. And then we're going to move every point up 1/3 of the unit. Okay? Again, you use your calculator to make sure that your graphs match. Do number 4? Sure. All right, so number 4, our points would be, you know, our parent function points would be -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And we said we're going to move 1 to the right, multiply the y coordinate by -1/2, and then move 1/4 down. So -2, 4. Move it 1 to the right. Take the y coordinate, which is currently 4, multiply by -1/2. So 4 times -1/2 would be -2. And then we're going to move it 1/4 of the unit down, so just barely a little bit down. What's wrong? When I multiply by -1/2, that automatically reflects it for me. So if I'm going to multiply by -1/2, I don't reflect because multiplying by the negative doesn't. If I were to reflect it again, then I've undone that.
You unreflected it.
Yeah.
Okay? So if you want to do the reflection, then reflect it, but only multiply by +1/2. Okay? It's like a double negative if you reflect it and multiply by the negative. Okay? All right, so then the point -1, 1, that's going to move it 1 unit to the right. Multiply the current y coordinate, which is 1, by -1/2, which puts me at -1/2, and then move it down just slightly. 0, 0 is our vertex, and there's symmetry here, so I'll be able to do some reflecting to simplify this process. I'm going to move that point 1 unit to the right, I'm going to take the y coordinate, which is 0, multiplied by negative 1/2, it's still 0, and then move it down a quarter, and then we'll reflect, and reflect. And here's what this parabola looks like. And if you wanted to get more points to get a better picture of this parabola, we certainly could do that. I mean, we would just pick some more points, like 3, 9. You could take the point 3, 9, do this stuff to it. It would give me another point that's a little bit further away to get a better picture of that parabola. Good one.
Yeah, can you grab that one? Just grab this one a little weird.
All right, number 5 is a cubic function now. So we're using the points -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. So our points are different because it's a different function. We are going to shift it 4 units to the left. We're going to multiply the y coordinates by -1, which is the same thing as reflecting over the x-axis. And then we're going to move it 1/3 unit up. So, doing this now, we're going to take the point -2, -8. And we're going to apply these rules. So I'm going to move 4 units to the right, excuse me, to the left. I'm going to take the current y coordinate, which is -8, multiplied by -1, that's going to put me at +8. And then I get to move up just a third. Next point is -1, -1. 4 to the left. Multiply by the y coordinate by -1, which gives me +1, and then up a third. Zero, 0. 4 to the left. I don't need to multiply by -1 because the y coordinate 0, and then up a third. 1, 1. 4 to the left. Multiply the y coordinate by -1, and then up a third. And then finally to 8. 4 to the left. Multiply the y coordinate by -1, and then up a third. There would be okay. All right, everybody okay? All right, the next family of functions that we're going to look at would be our square root and cubic root functions. And again, we got to pay real close attention to whether we're talking about a square root or a cubic root because they have different points. So we've got to be mindful of that. So let's do number 2. Got to get y by itself, so I'm going to divide by 2. So it's going to be a -2 square root of -x plus 1/2. What's our parent function? Right, square root of x. What are points that are on that square root function? That's 0 and 0. What else? 1, 1. 4, 2. 9, 3. Right? Those are points that we just need to associate with that square root function because those are the points that now we're going to transform based on what we can see in this equation. And so we'll start inside the function with that -x. What is that -x telling us to do? Reflect over the y-axis. Okay. Or we could think of it as multiply all the x's by -1. Right? That would do the same thing. Then we'll move to the outside. What about -2 on the outside?
1/2.
-2.
Oh, sorry. Negative 2y.
Negative 2y, and then move up 1/2.
Sorry.
That's okay.
I think we should keep it on.
We're going to go in this order. Reflect over the y-axis, then multiply the y-coordinates by -2, then move up 1/2 of the unit. Working with these points that we're going to have memorized as being associated with the square root function. So we'll take 0, 0. I can't really reflect that over the y-axis because it's on the y-axis. But then I'll take the y-coordinate multiplied by -2. Well, that's still 0. And then I'll move up 1/2 of the unit. All right, next one is 1, 1. Reflected over the y-axis. Take the y-coordinate, which is currently 1, and multiply it by -2 to get -2, and then come up 1/2 unit. Four, 2. Reflected over the y-axis, so that's going to be at -4, 2. Then take the current y-coordinate of 2 and multiply by -2, which is going to put me at -4. And then we'll move up 1/2 unit. And 9, 3. Reflected over. Take the current y-coordinate of 3 and multiply by -2, which will give me -6. And then move up 1/2. That would be that correct. Let me make up one real quick.
Which one did you? They say what's wrong with those. That's what I swear that's what she said. She said, what is wrong with you?
Let's make this a cubic root. We have 2 times the cubic root of 2x and then -3. I've already got y by itself for you, so don't have to worry with that.
Appreciate it.
We're dealing with the cubic root. What are points that are on the cubic root function? Right, -8, -2, -1, -1.
1, 1.
And what would be, we're going to start inside that function with the 2x. What am I going to do with that 2?
Multiply by all the x values.
We're going to multiply all the x's by
1/2.
1/2. We do the reciprocal. Then working on the way, working our way outside, that 2 on the outside, what am I going to do with that 2?
Multiply that by all y.
And then 3 down. And these are the points that we're using. -8, -2 is right here. I'm going to multiply the x coordinate, which is currently -8, by 1/2. And that's going to give me -4. And I'm going to multiply the y coordinate by 2, and I'll get -4. And then I'm going to move it down 3. Next one is -1, -1. Multiply the x coordinate by 1/2, I'm going to get -1/2. Multiply the y coordinate by 2, I'm going to get -2. And then move it down 3. 0, 0. I don't need to multiply either the x or the y coordinate by anything because it's 0. So I'll just move it down 3. One, 1. Multiply x by 1/2 and I get 1/2. Multiply y by 2 and I get 2. And then move it down 3. And the final point is 8, 2. So we'll multiply the x coordinate by 1/2 to give me 4. Multiply the y coordinate by 2 also gives me 4, and then move it down 3. Here would be this cubic root function.
So you couldn't tell, you could just go to like 27.
Yeah, you could have if you need to get some more points. All right, let's do a greatest integer function because this one's a little bit new to us. Remember that double bracket is the indication of a greatest integer function, and we know another name for the greatest integer function is the step function. Okay, so it looks like that staircase. So once we've graphed 2 or 3 of them and placed them correctly, then we should be able to establish the pattern for what the rest of that staircase looks like. Okay, so we need to start off by just remembering what is where does this kind of start, or what is that first step? And so I always start with the step that goes from 0 to 1. And remember, for the parent function, it always goes closed circle to open circle for each step. Now, if you look at number 1, and we'll just do that one because it's right there. What all are we going to do to this parent function? All right, we're going to multiply the y's by -1, move y up 2, and then go 3 to the right. And since that -3 is on the inside, I want to start there. So we'll go 3 to the right, then we'll multiply the y coordinates by -1. What else is this equivalent to? Yeah, reflecting over x. Okay, accomplishes the same thing. And then we'll move it up 2. So I'm going to take this entire step. It's not just a point that I'm working with now. I'm taking the entire step. I'm going to move it 3 units to the right. Then I'm going to reflect it over the x-axis when it's on the x-axis. So I'm not really going to do any reflecting. And then I'm going to shift it 2 units up. And so that step that went between 0 and 1 is now right here. And remember, for your parent function, you have a step that goes from 1 to 2, but it's at a y coordinate of 1. So there's the original. And then now I'm going to shift it according to these rules. 3 units to the right. Reflect it over the x-axis. Then shift it 2 units up. We have the step that goes from -2 to 3 at a y coordinate of 2. So we'll take that step and go 1, 2, 3 units to the right. Reflect it over. Move it up 2.
It's a lot harder when you can't.
Yeah. Definitely going to have to really visualize that. The nice thing about the step function is, I think once you've got 3 steps, then you can establish a pattern. And you can see that all of these are 1 unit apart. And so I think from now we'll just kind of do this. And I want you to go all the way to the edge of the graph. So there would be that staircase. Once you have 3 steps placed, then you should be in good shape to draw the rest. But it is, I do realize it is a little difficult. So it might be that for this step at 0, 1, you might move just the point at the origin. Move it, and then move the open circle at the point 1, 0, and connect that step. There's 1 step. Then go from 1 to 2, 2 to 3. So, started off. Yeah, I just started off with this. My parent function has a step that goes from 0 to 1. So I took that point, I shifted it the entire set 3 units to the right. And if I had to reflect it, then up 2. It ended up right there. All right, everybody good? All right. I think that's going to be everything for your test. Excuse me, your quiz tomorrow. I know in your quiz tomorrow you will have, I think it's 4 functions that you're going to graph. And then you're also going to have to, if I give you the equation, you're going to have to discuss the symmetry of that equation or that graph. You'll have to identify if it's a function or not. You'll have to tell me about the intercepts. And then you'll also have to be able to identify the domain and range both from the graph, but also from the equation. If I give you the equation, remember you're looking for things like square roots, denominators, for figuring out what x can be.
Is there anything of greatest?
Could be.